three mathematicians, Rivest, Shimar, and Adleman, were figuring out a way to transfer data securely between networks. At MIT in 1977, they established a type of encryption now called RSA encryption. RSA encryption lives up to its reputation as it uses large complex primes, making it hard to decipher, yet is based on a simple concept. RSA encryption is therefore used to transfer vital data. Such data includes password keys and hybrid digital signatures.
Alice wishes to send a valuable diamond to Bob, but the jewel could be stolen if it's sent unsecured. How can Alice solve this problem? To begin with, Bob sends Alice an unlocked padlock, which he would give to anyone who wishes to send him something. Alice uses Bob's lock to lock up the diamond before sending the box back, so Bob is the only one to be able to unlock it. This example demonstrates the underlying principle of the public key, cryptography. So how do they do it mathematically? Bob first comes up with unique numbers P and Q, which are only known to him. Multiplying these two numbers gives a public key N, and Bob also comes up with another prime number K. N and K are then publicized to the public, and Alice can then use them to encrypt her message M. This is done by the equation m to the power of k mod n congruent to C. This encrypted message C would then be sent to Bob, who can then decrypt this by using another private key E. Using the equation ek mod phi n congruent to 1, where phi n is equal to p minus 1 times q minus 1. Because of the mathematical difficulty in factorizing the large number n, people other than Bob would not be able to work out E. Finally, the equation c to the power of E mod n congruent to m would allow Bob to work out m. Bob sets off two values of p equals to 17 and q equals to 23. He makes n equals to pq, giving n equals to 391, and a public key k equals to 3, which is accessible by the public. He then finds out the value of phi n, which is equal to p minus 1 times q minus 1. Alice, who wants to encrypt a message m, which is equal to 123, uses the equation m to the power of k congruent to c mod n. She substitutes the values of m, k, and n, giving the value of c equals to 98. Which she passes on to Bob. Bob then uses another equation, ke mod phi n congruent to 1. Solving the equation gives a value of e, which is equal to 235. To find out m, he uses the equation c to the power of e congruent to m mod n. With the values of c, e, and n, he can now work out the message m equals to 123, whereas a public attacker cannot find out m because he does not know the value of e.
Now I'm gonna explain the math behind RSA encryption. PQE are private keys, KN are public keys. We are trying to prove C to the power of E is congruent to M mod N. That's how we code and decode message. By raising M to the power of K to the power of E, we can rewrite the claimant as the following. That's how we prove it. By Fermat-Little theorem, we have m to the power of p minus 1 is congruent to 1 mod p. By raising m to the power of p minus 1 to the power of q minus 1, we can get this equation, where 1 to the power of q minus 1 is congruent to 1 mod p. We can get the similar relationship for q by Fermat-Little theorem. Thus m to the power of p minus 1 times q minus 1 is congruent to 1 mod pq. And we note it as statement 1. Given that ke is congruent to 1 mod p minus 1 times q minus 1, we can rewrite it as some multiple of p minus 1 times q minus 1 plus 1 equals to ke. By substituting, m to the power of ek can be rewritten as following. Using law of indices, referring back to statement 1, it is congruent to m times 1 to the power of lambda mod pq, which is n, which is simply n. Thus, the statement holds.